Hello, my name is Harlow Babick, and this is my lab report on constant velocity. In this lab, I used the tracker platform to physically plot the change in position over time of a pencil pushed across a table. Then I used GlowScript to predict the position of the pencil using the average velocity derived from the tracker video. Inevitably, the observed and predicted positions are similar, with the observed position branching off slightly from the predicted about halfway through the time interval, suggesting that the pencil is moving close to constant velocity. In terms of models, I use the concepts of velocity and position update formula. You can predict final velocity by having the net force, initial velocity, and a short time interval. You can similarly predict r with using the same time intervals. Velocity update formula is derived from the momentum principle, which is F equals ma in its simplest form. Position update formula is based on the definition of velocity, which is change in position over time. It's important to know that the slope of a line of position over time is velocity, which is linear if it's constant. For the experiment, I used a video of a pencil being pushed and recorded the position at increasing time intervals, which eventually was plotted on a position time graph that had a slope equal to the average velocity. The system is the pencil, and notable surroundings are the table and the hand pushing. I'll discuss some of the initial conditions and findings soon. For coding, I wrote in all the initial conditions by finding the initial position on tracker, which was an initial position of 0.018 meters in plus y direction, and I also calculated average velocity from the first and last position of the pencil divided by time, which was 0.08 meters per second. Inside of the loop, I made two equations that are exactly the same as the position and velocity update formula, so that they would repeat for every value of delta t, which was 0.033 seconds, with the same total time interval as tracker, which was about 1.6 seconds. Here's a screenshot of my code. Inevitably, the velocity update formula didn't change velocity because Fnet equals 0. For the discussion, if I were to change the axis, the magnitude of the velocity would be the same, but if the axis was flipped, the direction would be flipped. Or if x and y were switched, the component that v was in would be switched. The pushes and pulls added together are the friction forces from the table and the applied force from the hand, and also normal force and gravitational force. In terms of the graphs, the observed line is pretty close to the predicted line, but shows a slight deviation, showing that the force in the observed video was not truly constant, perhaps from the applied force wavering in magnitude or friction. To conclude, I was able to watch an object moving at constant velocity using tracker to manually put the times, which I compared to a predicted model of scenario. By comparing these two, we can see that the pen was moving close to constant velocity because the forces are in equilibrium.